Wind power, of course, requires wind. The best place for wind is 1,200 feet above ground level, where there's always wind blowing. The strength and direction of the wind changes, but there is a constant wind there. And in fact, it is the local maximum wind speed nearest the ground. The speed of wind rises from the ground level to 1,200 feet, and then it actually begins to drop off after that. So 1,200 feet is the perfect place for the center point of a wind turbine. The problem, of course, is building a 1,200-foot tall wind tower. The chief problem with this, of course, is having adequate strength to resist the forces generated by the turbine. If a turbine is 1,200 feet tall, in general you'd want the blades to be 600 feet long. That represents an area of about 1.1 million square feet in what's called the disk, which is the area swept out by the blades, the circular area that the blades cover in turning. If it is desirable to produce electricity for wind speeds up to 40 miles per hour, there needs to be a safety factor, up to perhaps 60 miles per hour. 60 miles per hour is about 90 feet per second. If you square it, you get 8,100 feet per second. And if you divide by the magic number of 800, which is the density of air divided by gravity and divided by a factor of 2, the force on the disk is about 10 pounds per square foot. For 1.1 million square feet, that's about 11 million pounds of force. The wind tower itself would actually have to be founded in rock in order to resist all the forces and the overturning moments. That would mean that it would have to extend down into the ground, depending on how much the alluvium is before you reach solid rock. That could be an additional 400 feet. So you could have, in fact, have an effective height of 1,600 feet times 11 million pounds of force, or about 18 billion pound-feet of moment. To resist that moment, there's a thing called section modules. Section modules is often represented by capital S. It equals, for a circular ring, the radius squared times the thickness of the radius times pi. If the vertical power for the wind is 60 feet in diameter, 30-foot radius, that's about 2,800 feet, about 7 million pounds per radial foot of the ring times the thickness of the ring. If one allows steel of up to 50,000 pounds per square inch, which is fairly readily available, that would mean you need an area of about 144 square inches per foot, or about a 1 foot thick ring. Problem with this, of course, you then have to check for what's called thin-walled buckling, the actual displacement of the ring under loading, which can then lead to additional moments, which overloads it locally and causes a collapse. Additional bracing may be required inside the steel tube of the wind tower to prevent buckling. Going down into the rock, the other problem is the foundation. If you're loading it up at 50,000 pounds per square inch, rock cannot withstand that level of force, so you'd need to have a concrete footing also built into the bottom to spread out those loads so that the rock doesn't fail under the loads. To build the ring, it would have to be built in sections of perhaps 10 feet in height. That can represent a weight of close to 1 million pounds, at least at the base. The one way of building a structure of this form is to actually turn the vertical port tower for the wind turbine into its own crane. This would be accomplished by putting crane elements around the base of the crane, raising them into position, tying them together with cable. In between the elements, there would be steel springs to allow a little bit of movement and adjustment. There would also be some kind of pinning connections to prevent them from slipping past each other. The wires would be wrapped around the entire structure and then tightened to a very high load. Those wires would then provide the support that prevents them from separating. The entire object would have a lifting crane assembled on top of it. The crane would then be able to swing out past the tower, lift up an additional section, swing it into place, and then lower it onto the existing tower element. Tower elements would have to be built with fairly close tolerances, because the only way of joining the steel is probably with a process known as explosive welding, which is the detonation of an explosive charge against a piece of metal, and the shock wave moving through the piece of metal joins it to another piece of metal at the interface between the two pieces of metal. Conventional heat welding will not work with a piece of steel that thick, because you really can't adequately heat it and get an adequately strong weld, and the forces that would be developed by the tower are pretty enormous, and so a strong monolithic construction would be needed to hold the tower together under the extreme loads from the wind. The elements of the ring of the crane would be lifted into place, assembled, the cables would be tightened, and then additional cranes on the ground would then build the lifting crane on top. As it rises, sections would be swung into place, explosives would be used to join each section, and then it would be raised again. To help position the rings, a spider element could be used inside the tower, and the spider would have legs that would brace against the already assembled tower elements and would then reach up and help to grab the ring element and position it. The top part of the spider would then be able to rotate relative to the lower part of the spider element. It would then physically climb up another level to grab the next level of ring. It would be powered by electricity. The electric cable that is attached to the spider that enables it to crawl up when the tower is completed would be the power cable that would be used upon completion to connect to the generator and wind turbine to transmit the power for usage. When the top of the tower is reached, The spider would be picked up by the outer crane, lowered to the ground. A platform would then be raised in position, fitted onto the top of the tower, and then the generator element would be lifted up, and then the blades would be lifted up. On top of the generator element would be an installed crane. The crane would then be used to disassemble the crane elements from the outer crawler ring. A smaller crane would also be installed on that platform, and it would then help to dismantle the bigger crane. A smaller crane would then be disassembled and lowered to the ground in small loads. Workers could be carried up in a cable basket, which would have loops of cable around the tower to prevent it from swaying and moving excessively with respect to the tower, and would have wheels attached to it. There would be some tension in the cable that would wrap around the tower, and the wheels would be held against it. It would then be drawn up through a lifting mechanism in the entire ring part of the crane.